Hello and welcome to this lecture series on chemical process modeling and simulation. We have been discussing modeling energy of systems. In that, specifically after some brief introduction to thermodynamics, we obtained the criteria for thermodynamic equilibrium. We spent a video lecture trying to understand entropy, and then we spent a three-part lecture trying to understand intensive properties, namely temperature, pressure, and chemical potential. And then we are on to this two-part lecture on thermodynamic potentials. So in this second part of this lecture, we are going to consider how to obtain the various thermodynamic potentials corresponding to different specifications of the independent variables that are needed to define or specify the macroscopic state of a thermodynamic system. To quickly sort of recap what this all means, I would like to draw your attention to the state postulate, which says that the macroscopic state of a thermodynamic system may be defined by its internal energy or by entropy. Right, keeping with the internal energy formulation, because now we are looking at all different forms of energy, right? So keeping with the internal energy formulation, now you have to have how many independent variables are needed to specify the macroscopic state of a thermodynamic system. We need the number of independent work modes of energy exchange that are available for the system and the surroundings depending on the nature of the boundaries, plus 1, with the plus 1 being the mode of energy exchange by way of heat transfer. And therefore you have, for example, we wrote internal energy as a function of entropy, which captures the transfer of thermal energy by way of heat. Second, volume, which captures the exchange of energy between the system and the surroundings by way of displacement of the boundary. Right. And then the third, we specified the independent variable to be number of moles of the substance, or in some other form measure of the amount of substance that is present in the system, and that basically captures the mode of energy exchange between the system and surroundings, the work mode corresponding to a permeable boundary through which species can be, or the actual material can be exchanged between the system and the surroundings. So we saw all of these. Now the questions that we posed in the first part of the lecture is, can we come up with other choices of the independent variables other than S, V and N to determine the macroscopic state of a thermodynamic system? Now, what are the possibilities? For each mode, you have an extensive variable which we have identified, which are S, V and N respectively, for heat, moving boundary work and species transport work, right? So in addition to that, what are the other variables that are available? The corresponding intensive properties that are available, which are all partial derivatives of internal energy with respect to entropy leading to temperature, partial derivative of internal energy with respect to volume leading to negative of pressure, and partial derivative of internal energy with respect to number leading to chemical potential, right? So these intensive properties are available. Now what we asked ourselves is, can we use these intensive properties to specify or define the macroscopic state of the thermodynamic system, right? And we saw that the intensive properties are all not fully independent of each other. They are constrained by a relationship called Gibbs-Duhem relationship. Therefore, you have to have at least one extensive property that has to be used for specifying this macroscopic state of a thermodynamic system, which makes sense, because otherwise how do you know what is the size of the system, because the intensive properties are independent of the size of the system. So that information has to be carried in at least one extensive variable which is chosen as an independent variable. And therefore, we sort of then asked ourselves, how do we go from a specification like in entropy being the independent variable that determines whether the boundary is adiabatic where entropy is constant, or the boundary is diathermal where entropy changes. Now you allow for energy exchange, right? So in this kind of energy exchange that happens, what is the other variable that can be kept constant? The other variable that can be kept constant is temperature. Why? That is the case corresponding to the diathermal boundary. So when adiabatic boundary is there, your entropy is constant, there is no heat exchange, and therefore there is no TdS is 0, so ds is 0, S is constant. Now on the other hand, when you have a diathermal boundary, the criteria of thermodynamic equilibrium requires that temperature between the system of the system and the surroundings, or temperature of the two subsystems within a system which are in thermal equilibrium, they have to be constant. That means now I can choose different temperatures as independent variables. So that would lead to a specification of the state of the system by T, V and N instead of S, V and N. So can we go about doing this? When we are doing this change of specific independent variables to specify the state of the system, what are we essentially doing? We are replacing the independent variable entropy by the appropriate partial derivative of the internal energy with respect to entropy. So if you were to look at a function y is equal to f of x, now instead of saying y is a function of x, now I am saying y is a function of dy dx, which is the derivative of y with respect to x, and that is the slope. So if you were to imagine some sort of a function, right, any function for that matter, of y as a function of x, at each point you calculate the derivative, which means you get the slope of the tangent, right? Instead of writing a pair of points x comma y, x1 y1 x2 y2 x3 y3 x4 y4 and so on and so forth, what we are essentially doing here is we are writing dy dx at 1 y1, dy dx at 2 y2 and so on and so forth. So we are changing the independent variable from x to dy dx, right? X to the slope. So if I were to call the slope as m, then I would say m1 y1, m2 y2 and so on and so forth, right? So can I go about constructing some sort of a way to transform this one system, which is the x comma y, to the other system which is based on m, or the slopes, right? We concluded the previous part of this lecture by stating that Legendre transformations or Legendre transforms provide this shift, this transformed coordinate systems. And so now we are going to start in the next slide an understanding of what is Legendre transform, and then we are going to try and take one simple example to transform a function from the x comma y system to whatever is the system in the new coordinate system, where instead of x the independent variable is m. And then we will also see how to get the original function back, how to get the inverse, perform the inverse Legendre transformation, and then we will further use this to sort of go from the internal energy formulation to the various other formulations of thermodynamic potential. With that elaborate introduction and context providing sort of presentation, we now move to the mathematics of Legendre transformations. Now consider a function f of x. What is f of x? F of x is a mapping from this domain of set of all points x. For each x, you calculate what is f of x, that is the range. So the mapping from domain to range, all right, x comma f of x, this set of points gives the function. So this is how you plot a function. If you were to graph, say, where x-axis is x and the y-axis is f of x, and for each point x there is a corresponding value of f, and then you put all those points together and you construct a curve, that is the function, isn't it? This is what is the function. Now transforming x f of x, the mapping x f of x to one given by another set where the independent variable x is replaced by the slope at each point m, right? That is accomplished by Legendre transforms or Legendre transformation. The details are provided from the next slide. In thermodynamics, before we go into the actual Legendre transformation, it is important to recognize that such a mapping has to be one-to-one. In other words, going from this system to another system, okay, one based on x to another based on m, this transformation has to be one-to-one, so that you can uniquely match an entropy to a temperature and vice versa. This was the example that we were looking at. Instead of fixing s for SVN, we are going to fix the slope, which is the partial derivative of u with respect to x, dou u dou s Vn, right? So those are going to be T Vn, right? So the state of the system is defined irrespective of whether you use one variable, one set of variables, or another set of variables. Depending on the process, you know, it may be convenient for you to choose entropy, fixed entropy, or a fixed temperature. All right. So in an adiabatic process, the temperature will keep changing as you go through the process, whereas what is held constant throughout the process is that the entropy is held constant. When your boundary is a diathermal boundary, what you are doing is that you have established thermal equilibrium, and therefore the process that your system is subject to when your system surroundings boundaries are diathermal is an isothermal process, which means constant temperature, and therefore what will happen for that process, it is more convenient to choose temperature as the independent variable. So it is a matter of our what we are able to control, what we are able to measure. We can use these choice of variables. However, the information contained in u of s comma v comma n is exactly the same as whatever new thermodynamic potential that you are going to obtain, which is a function of t comma v comma n, right? So that information doesn't change. So if you have a certain information contained in one energy that defines the state of the thermodynamic system, and you want to represent the state of the thermodynamic system by a different energy, different potential, thermodynamic potential. So going from one mapping to another mapping, this has to be one-to-one, so that you can uniquely map entropy to temperature and vice versa, for example. Or it could be unique mapping of volume to pressure and vice versa. So this requires the function f of x to be monotonic in x. We will explain what this means in just a moment. Monotonic functions means what? If for any x there is a unique value of f of x, you don't see the same value for f occurring for multiple values of x, right? So this is a one-to-one mapping itself. So in other words, the requirement is that this mapping from domain to range, this itself has to be one-to-one mapping. Thankfully, all extensive thermodynamic functions depict this behavior. They are all monotonic functions of the independent variables, and therefore this is conveniently accomplished. I'll give an example just now. Consider a sinusoidal function. This basically is a contrary example. This is not a one-to-one mapping. So we are looking at f of x y, or f of x is equal to sin x, right? This is not a one-to-one mapping, right? Because if you put y equal to 0 or f of x equal to 0, sin 0 is 0, all right? So, but that is not only for x equal to 0. So you will get this value f of x equal to 0 for all n pi's, where n is integers, 0 plus or minus 1 plus or minus 2 and so on and so forth, right? So this is a many to one mapping. So many values of x result in one unique value of y, right? This is a contrary example of many to one mapping. Now, if you were to then use this Legendre transformation and map this mapping, okay, transform this mapping into another mapping involving the slope. At each point, you depict the system by the slope m or dy by dx. What is dy by dx? When y is sin x, dy by dx is cos x, right? So if we use cosine of x as the independent variable instead of x as the independent variable, and then you construct a new representation of mapping, all right, and then then you have to go backwards from that cosine x, some new capital Y for example, to x comma y. What kind of problems will we see? Notice that what happens is you cannot assign a unique slope for a given x. This is the problem, you see. So for any given x, y dash is cos x. Now let us see, is this a one-to-one mapping? Nope, it is not one-to-one mapping, because for all the points y equal to 0, y dash is either plus 1 or minus 1. 0, 2 pi, 4 pi, 6 pi, y dash is plus 1. Pi, 3 pi, 5 pi and so on and so forth, y dash is minus 1. Now if you were to go from your m, which is this, back to x, your original independent variable, this mapping you have one value of plus 1, for which x does this plus 1 correspond to? Does this correspond to 0 or 2 pi or 4 pi or 6 pi or 8 pi? You don't know. There is no way to know. That information uniqueness is lost. Therefore, the inverse mapping becomes one value, which is plus 1, to many values of x, 0, 2 pi, 4 pi, 6 pi, 8 pi. So this, when your individual function itself, the choice of this function, isn't it? This function, when it is not monotonic, then this Legendre transformations and inverse Legendre transformations do not fully preserve the information that is contained in the function itself. Whereas if I were to choose any monotonic function, y equal to x square, for example, I can go back and forth without any loss of generality, right? Any loss of information. So this we will see in the next slide, how to construct a Legendre transformation, and we will choose a monotonic function to explain how this transformation is constructed and how the inverse transformation is obtained. Consider a monotonic function, say y is equal to e power 2x. Exponential function is a monotonic function, it's a one-to-one mapping. So what is the slope? Slope y dash m is 2 e power 2x, which is simply 2y. So here is a curve like this, a monotonic function, right? Actually, this part doesn't seem monotonic, but I have still gone ahead and used it because this was the best, closest one that I could take, where there was a point and a nice tangent to it, were all drawn and all that, right? So this point is, of course, the y-intercept corresponds to x equal to 0, and I'm denoting this intercept as psi, right? And note that this psi is also along the y-axis. In other words, if you were to consider this mapping and you say x comma y, for each value of x there is a unique value monotonic function, so unique value of y, right? Similarly, if I were to consider a set of all values of, instead of y, a set of all values of psi, they also lie along the y-axis only. Just keep in mind, that's important. Suppose we want to construct a Legendre transformation of y. Consider any point x comma y. The equation of the tangent to at that point, tangent to the curve, tangent at that point, not to that point, is y is equal to mx plus psi, where m is the slope, which is dy dx, psi is your intercept, right? Slope intercept form of a straight line for the tangent. Y is equal to mx plus psi. Note that psi has the same units as y. That's what I was trying to explain. The set of all points psi lie on the same axis as set of all points y. They both have to obviously have the same units, and that's important. In other words, the set of all points y and the set of all points psi are the same. If y were the energy of the system, psi is also energy of the system. It's just a different energy. For example, for this particular value of x, y is this, that is one energy, but psi is this, that's a different energy, but nonetheless they both are energies. Thus, now going back to coming to this equation, there is some unique function, monotonic function y equal to some f of x, and then you write the you get the tangent to that function at any point. Now what you can do is, instead of mapping of x comma y, instead of x I am going to use the slope, which is the dy dx, right? So since the function is a monotonic function, now what I will do is I will get multiple values of slope at different points, right? So I will have each value of x will have a unique value of m, and the corresponding y, instead of choosing y, I am going to choose the intercept, y intercept. So the same function, instead of y equal to y of x, may be expressed as psi equal to psi of m, where this is a unique transformed function for this y equal to y of x. This is the Legendre transform. This is the Legendre transformation. How do you construct this Legendre transformation? Very simple. Just write psi equal to, psi is of course defined as y minus mx. That is the definition of the transformation. Now for example, if you were to do this, what are you going to do? Obviously your psi has to be a function of m alone, so you must eliminate y, you must eliminate x. How do you eliminate both? Express y as a function of m, x as a function of m. Y as a function of m is very straightforward. Y is equal to simply m by 2, which is what has happened here, and then there is a m here which corresponds to this m. Now I have to express x as a function of m. For that I can use this expression, m by 2 is e power 2x. Now I take ln on both sides. Ln of m by 2 is 2x. So x is half ln m by 2. So that's what I have done. So now I have a unique function psi is equal to psi of m, and this is my Legendre transform. Very simple. Y minus mx, that's it. So the Legendre transform of y equal to e power 2x is psi equal to m by 2 minus m by 2 into ln of m by 2. Clear? Now, when we construct Legendre transforms of monotonic functions, we can recover the original function by performing an inverse Legendre transform. Now you start with this transformed system, psi equal to psi of m. Now you have to get y equal to y of x. Alright. So what is the corresponding y equal to y of x for this? Y is e power 2x, right? So that's what you have to get. Keep that in mind. Sorry, I did not do the animation properly. So, but we know that psi is equal to y minus mx, and therefore we can write what is d psi. D psi is dy minus m dx minus x dm. But you know m is dy dx, so basically dy is m dx, so these two will get cancelled. So simply d psi is equal to minus x dm, and that gives us, for unique monotonic functions, okay, so the inverse Legendre transform may be obtained by saying d psi dm is equal to minus x. So now what is this? Is our psi. Let's take the derivative d psi dm. So for this you will get a half. For this you will get two terms. So if you first differentiate with respect to m by 2, so you will get half ln m by 2, and then the second term you are now going to keep m by 2 and then differentiate ln of m by 2. So that is going to give you basically minus m by 2 into 1 by m. So all of this is going to simplify to the basically you are going to get half here, and this half and that half will get cancelled. You will get x equal to minus half ln of m by 2. So now from this, now you can convert m back to x. This gives us m is equal to 2 e power 2x. So basically negative sign and negative sign will get cancelled. So ln of m by 2 is 2x. M by 2 is e power 2x. So m is 2 e power 2x. So I can now substitute m. Now what have I done? I've come halfway. I have expressed psi as a function of x. But then I have to now get my y. How do I get my y? The inverse Legendre transform is constructed as follows. Y is simply mx plus psi. Alright. So now I have constructed a psi as a function of x. I already have m as a function of x. I just substitute all of it, simplified, and I get e power 2x. So if you were to look at it, the Legendre transform is given by psi is equal to y minus mx, which is one way of writing the equation of this tangent. The inverse Legendre transformation is constructed as y is equal to mx plus psi, which is another way of writing the same equation of the tangent. So the key is we are just using the equation of the tangent to go from x comma y to psi m comma psi. This is the transformation that we are doing. So thus we have recovered the original function. Now we start defining one thermodynamic potential after another. It all becomes very easy once you understand what is happening here mathematically. Suppose we choose the independent variables S, P and N to define the state of the system instead of U is equal to U of S, P and N. So defining the energy exchange due to expansion by pressure instead of volume. That's what we are doing. So what are we doing? We are changing the independent variable corresponding to energy exchange due to expansion or moving boundary. So we have changed that independent variable from volume to pressure. Okay, so pressure is of course the slope, minus m is minus dou u dou v, and therefore this will require a Legendre transform to determine the thermodynamic potential, new thermodynamic potential that will define the state of the system. This potential we call as enthalpy. Okay, so psi is y minus mx, that's m is minus p basically, right? So u, what is your original one? Y is y of x, right? Now we are writing psi is psi of m. Only one variable is changed, other variables are held constant, right? So v is becoming p. So what am I doing? Y, but instead of y I am writing u, and instead of m I am writing minus p. And of course, what is the independent variable I have changed? I have changed the volume to pressure. So u minus pv, this becomes u plus pv. So enthalpy is defined as u plus pv. So this is a set of all energies. Just as this is a set of all energies, both are the y-axis. They define the macroscopic state of the thermodynamic system. It is just that these energies correspond to the intercepts, which are captured from slopes, the equations of the tangents when I'm expressing this energy exchange by way of the slope instead of the independent variable. So enthalpy is the energy stored in the system, again potential and kinetic energy, when the system has adiabatic, moving and impermeable boundaries with its surroundings. So this is the enthalpy, this is the energy that we calculate. Note that the internal energy therefore is the energy stored in the system when the system has isolating boundaries with the surroundings. That's what we did, that's what we started, and then we started relaxing the various boundaries, the types of boundaries, and then we obtained the various the criteria for thermodynamic equilibrium. So we started with isolating adiabatic rigid impermeable boundaries, so there is no energy exchange, and so we defined, I added all the potential and kinetic energies, and then we said, hey, I'm calling this as internal energy. Now I'm changing one by one. For each I will get new thermodynamic potentials. So when I change the specification of the volume of the system to the slope, which is the pressure of the system, slope of internal energy with respect to volume, now I get a new thermodynamic potential. That potential is enthalpy. So that the boundary is made moving means that the rest state or the equilibrium state is the one where the pressures of the systems and surroundings are the same. In other words, the system is in mechanical equilibrium with the surroundings. So this equilibrium state, the rest state of mechanical equilibrium, defines the state of the system. Therefore, that is defined by the pressure, and therefore pressure becomes the independent variable. Now I can move to a new equilibrium state which will correspond to a different pressure, so on and so forth. So what are the fundamental equations of state? In the first part of the lecture, we obtained the differential and integral fundamental equations of state of Euler for internal energy. Now what are the fundamental equations of state for the system that has adiabatic, moving and impermeable boundaries? So in other words, what are the fundamental equations of state for enthalpy? H, of course, is U plus PV. U is Ts minus PV plus mu1 plus PV. So this PV and PV will get cancelled, and therefore this is the integral fundamental equation of state. Now I can take a derivative of this. All right. So dH is equal to du plus PdV plus VdP. That is, du is TdS minus PdV plus mu dN plus PdV plus VdP. So the minus and plus PdVs will cancel, and therefore dH is TdS plus VdP plus mu dN. This is the differential fundamental equation of state. I hope this is clear. So what does this mean? Imagine the surroundings to be an infinitely large system, like for example an atmosphere at a fixed pressure, and so the system is always in mechanical equilibrium with the surroundings. So there is a fixed pressure. So now if you change this pressure of the atmosphere, external pressure of the atmosphere, then you will essentially allow for re-equilibration, and a new equilibrium state will be reached for the system with a different pressure. The energy content will correspondingly change. And this is the idea. So H is H of S, P and N. The independent variables are entropy, pressure and number. Now, there is also another context in which enthalpy is used to describe the state of thermodynamic system. In your earlier courses in thermodynamics, you may have encountered this. This is when there are flow systems where there is no change in composition, either due to flow or due to any other process that may take place in the system. So basically N is fixed. When I am saying no change in composition, N is fixed. This means no phase changes, no mixing, no separations, no reactions. N becomes a fixed parameter. In such a situation, the independent variable associated with the flow can then be simply seen as pressure, because bulk flow occurs from regions of higher pressure to those of lower pressure, and at every cross section along the direction of flow there is fixed pressure. Pressure here, pressure here, pressure here, pressure here, and so on and so forth, right? So the appropriate thermodynamic variable for this system at every point is one of pressure, the independent variable, and therefore the energy content is best captured by enthalpy. So this enthalpy is used for flow systems with no composition changes. Now we turn our attention to the next thermodynamic potential, Helmholtz free energy. Suppose we choose the independent variables temperature, volume, number to define the state of the system instead of entropy, volume, number, which will of course result in the energy of the system which defines the macroscopic state of the thermodynamic system to be internal energy. Now, what will be the energy if we choose temperature, volume, and number? So now once again we are defining this mode of energy exchange by virtue of heat transfer, by temperature, which is the slope dou u dou s, instead of the independent variable entropy s. So we are replacing s by the slope dou u dou s, which is temperature. So this will require a Legendre transform to determine the thermodynamic potential that will define the state of the system. Now this potential is called the Helmholtz free energy. Once again, the Legendre transform, the transform potential would be psi defined as y minus mx, where y is u and m is the slope temperature and x is the independent variable that was originally you used for defining the internal energy, which is entropy. So this gives us u minus ts, and that is defined as Helmholtz free energy. Helmholtz free energy has multiple symbols that are used in textbooks, but the most common one is A. So I have retained A here. So Helmholtz free energy is the energy stored in the system, again both potential and kinetic energy, when the system has diathermal boundary, rigid and impermeable boundaries with its surroundings. So therefore, the rest state of the system will correspond to the system being in thermal equilibrium with the surroundings, which means that the temperature of the system is constant, and whenever the surroundings temperature changes, correspondingly the system's temperature also will change, and thereby you can have a set of temperatures that define the state of the system, particularly with respect to energy exchange due to heat. So Helmholtz free energy arises when the boundary is made diathermal, and therefore the rest state of the system is the one in which temperatures of the system and surrounding are the same. In other words, the system is in thermal equilibrium with the surroundings, and therefore the temperature is fixed, and by changing the temperature of the surroundings, so you have temperature being the independent variable. So this was similar to the arguments made for enthalpy. Now similarly, what are the fundamental equations of state for the system that has diathermal, rigid and impermeable boundaries with its surroundings? By our definition, A is u minus Ts, that's the Legendre transformed potential from u, that is your Helmholtz free energy. But u is from Euler's integral fundamental equation of state, Ts minus Pv plus mu n. You subtract Ts, and therefore A is minus Pv plus mu n. Now if you were to differentiate this, dA would be du minus Tds minus sdt, but then du itself is Tds minus Pdv plus mu dn, and then you subtract Tds and sdt from it. The Tds terms get cancelled, and therefore this results in the differential fundamental equation of state for the infinitesimal change in Helmholtz free energy, and you see that the independent variables are temperature, volume and number. So once again, what does this mean to have temperature as the independent variable? So imagine the surroundings to be an infinite thermal reservoir at a fixed temperature. A typical example of this is a water bath that is oftentimes used to maintain constant temperature, right? So changing the reservoir's temperature allows for re-equilibration. So A is a function of T, V and N. Now the next one is Gibbs free energy. Suppose we choose the independent variables temperature, pressure, number, and so this basically becomes an isothermal system, isobaric system, constant pressure system, and this is basically the typical thermodynamic potential that is chosen when we have oftentimes phase equilibria and reaction equilibria, right? So to define the state of the system, instead of say S, P and N, so we take enthalpy, and then do a Legendre transform of the independent variable entropy to temperature. Or we take Helmholtz free energy T, V and N, we do a Legendre transform of volume to pressure. Either way we look at it, we will get this new thermodynamic potential. So keeping the starting point to be enthalpy, so we essentially do a Legendre transform to convert to express the state of the system. Instead of by entropy, pressure and number, we replace the independent variable entropy, the extensive variable entropy, by its corresponding intensive variable, which is the slope, which is this slope dou h dou s, which is the temperature. And then this will require a Legendre transform to determine the thermodynamic potential. By the same arguments as before, this potential is Gibbs free energy, and so the Legendre transform is defined by psi is y minus mx. Now your starting point y is h, enthalpy. Your independent variable, extensive variable, which is transformed by its slope is entropy, and the slope itself m is temperature. So this is basically the new potential is h minus ts. This is called G, and you could have done something similar with the starting point being A and Helmholtz free energy, and you would be transforming volume. Instead of volume, you'll be using pressure. The slope itself is negative of minus p. Dou A, dou V is minus P, and therefore you would have gotten A plus PV. So G is H minus Ts or A plus PV or U plus PV minus Ts, whichever way you want to look at it. So Gibbs free energy is the energy stored in the system. Again, potential and kinetic energy when the system has diathermal wall, moving wall and impermeable walls. Oftentimes this is also the case. Instead of moving boundaries, it's also a diathermal, and open boundaries also could result in Gibbs free energy being the appropriate thermodynamic potential to define the specify the state of the macroscopic state of the thermodynamic system. So Gibbs free energy therefore defines the macroscopic state of a thermodynamic system when the system has diathermal, moving or open boundaries and impermeable boundaries. Meaning, now you have the option of number being fixed or exchanged. So again, by the same argument, the boundaries made both diathermal and moving means that the state of the system is the one in which temperatures and pressures of the system and the surroundings are the same. In other words, the system is in both thermal and mechanical equilibrium with the surroundings. Now, if we allow for the number also to exchange, then we will reach chemical equilibrium as well. Then the overall the system will be in thermodynamic equilibrium. Now, what are the fundamental equations of state for the system that has diathermal, moving and impermeable boundaries with the surroundings? We start by writing G is H minus Ts, H is Ts plus mu n, and then you subtract the Ts, and therefore G is simply mu n. And this sort of, is the integral fundamental equation of state. Now, if you were to take a derivative of G, dG would be dH minus TdS minus SdT, but dH itself is TdS plus VdP plus mu dN, and then you subtract these two terms. The TdS terms get cancelled, leaving dG is equal to minus SdT plus VdP plus mu dN, this being the differential fundamental equation of state. So you see that G is a function of T, P and N. So imagine the surroundings to be an infinitely large system like an atmosphere at a fixed temperature and pressure. So you have an open mechanical equilibrium as well as thermal equilibrium, and changing this Tp allows re-equilibration. And so we see that G is a function of temperature, pressure and a number. One of the important consequences of Gibbs free energy is this chemical potential, which is now defined as partial molar Gibbs free energy at constant temperature and pressure, both of which are measurable and therefore controllable in a process, rather than entropy and volume, To fix volume, it's not that difficult. We have to make all the boundaries rigid, but fixing entropy is not always a given. All right. So therefore, chemical potential is partial molar Gibbs free energy, really, at constant temperature and pressure. And these fixing temperatures and pressures are the common ways in which chemical reactions take place, or in which phase changes take place in chemical engineering, and therefore this definition of chemical potential is very useful. Now, on the other hand, if your reaction were to take place in a calorimeter, for example, a bomb calorimeter kind of a thing, a system where if you can fix the volume of the system, gaseous reactions, which therefore gases expand to occupy the entire volume, for example, then you would have minus S dt plus mu dn, but you will have minus PdV. Then the appropriate thermodynamic potential would be Helmholtz free energy, and chemical potential would again be the partial molar Helmholtz free energy at constant temperature and volume. So both these definitions of chemical potential, as you can see, these would be the partial derivatives, right? Dou G dou T at constant Pn would be minus S, dou G dou P at constant Tn would be V, and dou G dou N at constant Tp would be mu, right? So this definitions of chemical potential is practically very relevant. This is the thermodynamic potential for open systems. So with this, we come to the end of this lecture on thermodynamic potentials, the two-part lecture. I hope you have been able to follow all the ideas contained in this lecture. Now, if I'm always available to answer any questions, any doubts, any clarifications, and I would also welcome feedback, comments on this on the content and the presentation of these lectures. So you can reach me either on the comment section of the YouTube channel, or you can write to me otherwise, and I'd be very happy to receive feedback from you. Thank you for listening to this lecture. I hope you have a wonderful day. Thank you very much.